Hi everyone, welcome to the first video for week 1 of the categorical data analysis class. Just to give a brief background of the course, the first half of this course describes some standard methods of categorical data analysis developed prior to about 1960. These include basic analysis of association between two categorical variables or even three variables, usually in the form of tables. The latter half of the course introduces models for categorical responses. These models resemble regression models for continuous response variables as was discussed in your regression course. These are special cases of a generalized class of linear models, which we will discuss later on, that also contains the usual normal distribution-based regression models. The main emphasis of this course, the latter half, is on logistic regression models. So now, let's just define some of the basic terms that we need in categorical data analysis. A categorical variable is one for which the measurement scale consists of a set of categories. So there are two primary types of categorical variable, the nominal and the ordinal variable. A nominal variable is a categorical variable having unordered scales, while the ordinal variable is a categorical variable having ordered scales. Categorical data consists of frequency counts of observations occurring in the response categories. So to add some more terms, let x and y denote two categorical variables with I and j levels respectively. So they would have I times j possible combination of outcomes, which are represented by the cells in a rectangular table of I rows for the categories of x and j columns for the categories of y. Here, we will have a contingency or a cross-classification table, which is a table in which the cell contains frequency counts of those outcomes. So we have a two-way table which cross-classifies two categorical variables, and then we have a three-way table to cross-classify three categorical variables, four-way table for four variables, and so on. So here's an example of a two-way table, wherein the row variable is about the group, which is either placebo or aspirin, and then the column variable is having myocardial infarction or not. So let's have a description of this table. The table is taken from a report on the relationship between aspirin use and myocardial infarction by the Physicians' Health Study Research Group at Harvard Medical School. The Physicians' Health Study was a 5-year randomized study testing whether regular intake of aspirin reduces mortality from cardiovascular diseases. So every other day, physicians participating in the study took either one aspirin tablet or a placebo. This study is a double-blind study, meaning both the patient and the physician who's giving the medicine does not know whether they are giving placebo or taking placebo or aspirin. So now, let's go to the concept of discrete and continuous variables. So this is very important since I've seen a post in a social media platform describing discrete variables as variables whose values needs to be integers. But that is a very incorrect definition. So here, variables are classified as discrete or continuous according to whether the number of variables they can take is countable. Remember, what we need or what would there mean whether a variable is discrete or continuous is whether it is countable or not. Actual measurement of all variables occurs in a discrete manner due to precision limitations in measuring instrument, because technically everything is countable if you're using a measurement that has say a ruler which only uses the units in centimeters or in inches. So each of the lines there would be specific values, meaning there would be just a countable number of measures that you would get. Unlike in the continuous side, wherein you could have 1.0856693 as an example. Okay? The discrete continuous classification in practice distinguishes between variables that take few values and variables that take lots of values. So technically, you could consider a variable that takes on integers as a continuous variable if the number of values that it could take on is quite large. For instance, statisticians often treat discrete interval variables having a large number of values such as test scores as continuous. For example, you have a exam that is from 1 up to 500 or 1 up to 200. Since there are, if that it's a 200 item test, then you could have 0 to 200, so you have 201 possible values. That is quite large, so you could already consider it as continuous in the treatment of that data. Okay, so you could use methods for continuous responses. So if you have a variable that is characterized by an integer, then it is not necessary that it falls under the lessons that we will be discussing. Because in this course, we will be dealing with certain types of discretely measured responses. First one is a binary variable, meaning it takes only two values. Nominal variables, as defined earlier, it takes on more than two values, but there's no ordering. Then ordinal variables, categories which are in order. Then we have here number 4 and 5, as you could see. 4 is discrete interval variables having relatively few values. The concept of having few values is quite subjective. You could have 10 values, 20 values, depending on the situation. You could treat that data as discrete, or you could treat that as continuous. Okay, maybe you could do some hypothesis testing or some assumptions checking whether it would the methods for discrete or continuous data would apply. And lastly, continuous variables group into a small number of categories. As you could see here, technically we are just converting a continuous variable into, say, an ordinal variable, since you will be having groups, but these groups are in a certain order. So now we will go to some of the concepts in probability and inference that you need in the discussion of categorical data analysis. The first thing that you need to recall is the concept of the binomial distribution, because of course we are dealing with binomial kind of data, meaning there are two values, so we need the binomial distribution. A random variable x is said to have a binomial distribution, which is denoted by here, x tilde bi and p, if can be viewed as a total number of successes out of n independent and identical Bernoulli trial with probability of success equal to p. Recall, Bernoulli trial is a trial wherein there are just two possible values in that experiment. Say, for example, tossing a coin, you will either have a head or a tail. So that is a Bernoulli trial, and then you will conduct that trial n number of times independently, and it must be identical, and then you must know the probability of success, or the probability of having the first response. So the probability mass function of the binomial distribution is given by the equation that you could see, where the two parameters n and p must satisfy that p should be in between 0 and 1, since it is a probability by definition of probability, and n ranges over the positive integers. Of course, since you are counting the number of trials, you cannot have 0 number of trials or a negative number of trials. And then please take note that the 1 minus p in the equation is often denoted by q. So q is equal to 1 minus p, where p is the probability of success, or the probability of getting the first category. So the next distribution is the multinomial distribution, which is usually attributed to the nominal type of variables. In a multinomial experiment, x sub I denotes the number of trials out of n wherein the resulting outcome is E of I, wherein I is from 1 up to k plus 1. Then, we have the random variables x sub 1, x sub 2, up to x sub k, wherein these are the number of trials that resulted to the ith outcome. Here we have x1, x2 up to x sub k because, as you would recall in your probability course, if you have k plus 1 number of categories, determining the number of outcomes for the first up to the kth category would determine the number of outcomes for the k plus 1 category. In some cases, the definition here is x1, x2 up to xk minus 1, and then you will exclude x sub k. But here, in our definition, we will be having k plus 1 number of categories. That is why we are including x sub k in the listing of random variables. So, if we have this sort of experiment, then we have the multinomial distribution, which is a joint probability mass function given by the equation below. As you could see here, the joint PMF is just the combination of n taken each of those number of results for each category times the probability of getting that ith outcome raised to the number of results or number of trials that resulted to that outcome up to the probability k plus 1 raised to x k plus 1. And here, of course, we have two constraints. First, the sum of the x sub i's, I from 1 up to k plus 1, should be equal to n. Of course, the total number of results should be equal to the total number of trials. And the sum of each of the p sub I should be equal to 1, since it is still by definition of probability. If there are k plus 1 number of outcomes, then they must share the entire probability space within p sub i's. So the sum of the p sub i's should be equal to 1, since there are no, it is impossible that you would not lead to at least one of these outcomes. So just some notes to remember. The binomial experiment becomes a multinomial experiment if each trial can have more than two possible outcomes. So you could easily see here the relationship between a binomial experiment and a multinomial experiment. Hence, the connection between the binomial distribution and the multinomial distribution. Second, the PMF of the multinomial distribution gives the probability that the outcome E sub 1 occurs exactly x sub 1 times. The outcome E sub 2 occurs exactly x sub 2 times, and so on, up to the k plus 1 outcome, which occurs exactly x sub k plus 1 times in the n independent trials. So you could recall the constraint that I mentioned a while ago, that the sum of the x sub i's should be equal to n, and then the sum of the p sub i's should be equal to 1. Next, the multinomial distribution has k plus 1 parameters. So as you could recall, if there are k plus 1 outcomes, there are k number of random variables. But we still have k plus 1 parameters because we have n, which is the number of trials, and then the k other parameters, which is p sub 1, p sub 2, up to p sub k, which is the probability of resulting to that ith outcome. Remember, the quantity p sub k plus 1, like in the binomial distribution, we have only n and p, is not a parameter because we know that if we add up p sub 1 up to p sub k and subtract it to 1, as you can see here, you would have the value of p sub k plus 1. And then lastly, this for the relationship of having a multinomial distribution, how could you simplify? If x sub 1, x sub 2, up to x sub k has a multinomial distribution, then each x sub I is binomially distributed. Meaning, you could have an experiment or consider an experiment that is either the ith category or not that ith category. So it's a success or failure situation. Success if it's in the ith category, failure if it is not in that ith category. So every x sub I could follow a binomial distribution with n number of trials and p sub I as the probability that the outcome would be that uh, x sub I that we are talking about. Now, for having value or variables with having relatively few number of possible outcomes, then we have the Poisson distribution or the Poisson distribution. Sometimes count data do not result from a fixed number of trials. For instance, we want to have the random variable y, which is the number of automobile accidents today on EDSA. Since there's no fixed upper bound n, which is basically the number of vehicles that will be going through EDSA, for y must take a non-negative integer value and its distribution should place its mass on that range. So the simplest distribution for this kind of situation is the Poisson distribution. Its probabilities depend on a single parameter, which is the mean, mu, and the PMF, or the Poisson distribution, is given by the equation below. You could see it is e to the negative mu raised to y over y factorial. Here, y could take on values 0, 1, 2, and so on. So you could see these are integers which has no upper bound. So some things that you need to recall about the Poisson distribution. First is that it's a random variable that has an equal mean and variance. As you can see, we only have one parameter, and that is the parameter for both the mean and the variance. Meaning, it is unimodal with mode equal to the integer part of our mean. The Poisson distribution approaches normality as mu increases. Meaning, as you increase the value of the mean, the Poisson distribution would look like a normal distribution. I think this illustration was already shown in your Stat 210 course. Okay, so the normal approximation is being quite good when mu is at least about 10. As you could see, the mean value need not to be very large. At least 10, we would have a good approximation of the normal distribution coming from a Poisson distribution. So fourth, the Poisson distribution is used for counts of events that occurs randomly over time or space, because we are not establishing the upper bound for the possible values. So it's just how many instances would this certain event occur during a certain time or in a certain area, when outcomes in these joint periods or regions are independent, as you could see. It also applies as an approximation for the binomial when n is large and pi is small. Remember, the binomial distribution counts the number of successes in a Bernoulli trial, meaning there could be a success or failure. So you could see here, if there's a large number of trial, and then there's a very, very small chance of having a success, you could see there is a connection between the Poisson and the binomial distribution. Meaning, the Poisson distribution could be used if we are looking at rare events. And in this case, we have here the mean of the Poisson distribution being equal to n times the probability of success in the form of the binomial distribution. To give a better illustration, or to make you recall the lessons that was discussed in your prob course, either in Stat 231 or 221, here we have an example. Suppose y is the number of deaths today in auto accidents in Metro Manila. So hence we have no upper bound. So for example, if each of the 5 million people driving in Metro Manila in a day is an independent trial with the probability equal to 0.000003 of dying today in an auto accident, then we could have a binomial distribution for our y, which follows binomial with n being equal to 5 million and p being equal to 0.000003. So as you could see, this can be viewed as a binomial, but this could also be viewed as a Poisson distribution with mean equal to the product of n and p being equal to 50. So this could be viewed as a scenario where y follows a Poisson distribution with mean equal to 50. So a key feature of the Poisson distribution is that its variance equals to its mean, as we've already stated in the previous remark. So sample counts vary more when their mean is higher. As you can see, the variability is dependent on the mean. So the higher the mean, the higher the variance, meaning the more spread the values could be. But if we are dealing with a Poisson distribution with a very low mean, say 2, then the spread of the values is also small. That is also the reason why if we have a mean value that is quite high for the Poisson distribution, it would have a variance that is large enough to approximate a normal distribution. Okay, so here, when the mean number of daily fatal accident equals 15, greater variability occurs from day to day than when the mean equals to 2, as I've already said. So the next distribution that you need to recall is the chi-square distribution. So this distribution is not attributed to a random variable that we will be dealing in categorical data analysis. But most of the hypothesis testing methods that we will be using uses the chi-square distribution. So, yeah. Another distribution of fundamental importance for categorical data is the chi-squared, not as a distribution for the data, but rather as a sampling distribution for many statistics. If you would recall from your inference course, you are using the chi-squared distribution for um, likelihood ratio tests, and you could also use the chi-squared distribution for the Walls test. So yeah, because of its importance, we summarize here a few of its properties. First, the chi-square distribution with degrees of freedom equal to the mean, and then variance equal to 2 times the degrees of freedom, and its skewness is equal to the square root of 8 divided by the degrees of freedom. So mean is equal to the degrees of freedom, variance is equal to 2 times the degrees of freedom, and skewness is equal to the square root of 8 over the degrees of freedom. Next, it converges slowly to normality as the DF increases. Remember, you could see here, if you are increasing the DF, you are also increasing the variance because variance is equal to 2 times the degrees of freedom. Having a large DF, we will have more variability and allowing a more of a normal-like distribution. So as you can see, it converges slowly, there's a note here, slowly to normality as the DF increases. The approximation being reasonably good when DF is at least about 50. Okay, so that is the main takeaway here. The DF should be at least about 50 before we could approximate the normal distribution from the chi-square distribution. It requires a large DF because naturally the chi-square distribution is skewed and the normal distribution is symmetric. So we want to increase the variance so that the skewness from the chi-square distribution almost diminishes due to variability. Okay, some additional connection of the chi-square distribution with other distributions. Say, let Z denote a standard normal random variable, meaning it follows the standard normal distribution, which means it has a mean equal to 0 and the variance is equal to 1. Okay, So if we have a random variable that follows a standard normal distribution, if we square that random variable, we will have z squared in this scenario. It follows chi-square distribution with 1 degree of freedom. So remember that if you square a random variable that is of the form of a standard normal, you would have a chi-square random variable with df equal to 1. Next is this scenario. A chi-square random variable with df equal to b has the representation of z1 squared plus z2 squared up to plus zb squared, wherein c1 up to cv are independent standard normal random variables. Meaning, if you have a chi-square random variable, you could express it as a sum of the squares of standard normal random variables. But the decomposition of this is quite difficult. That is why what we will be usually seeing is that third remark. A chi-square statistic having df equal to v has partitionings into independent chi-square components, as we could recall from the second remark. But conversely, the reproductive property states that if we have the square of x1 and the square of x2, wherein both x1 and x2's are chi-square random variable, if we take the sum of two chi-square random variable, we will have another chi-square random variable, but the degrees of freedom of their sum is the sum of their individual degrees of freedom, as you could see here. Here, you would see x1 squared has v sub 1 degrees of freedom, x sub 2 squared have v sub 2 degrees of freedom. So if you get a random variable, which is a result of their sum, the df of the chi-square is just the sum of the degrees of freedom of the x sub 1 squared and x sub 2 squared. So after reviewing some concepts needed about the distributions for categorical data analysis, we'll now revisit some concepts, say joint probability, marginal probabilities, and conditional probabilities, and the concept of independence, but we will view them in the perspective of contingency tables. So to start with the illustration, first let's create an example. Suppose uh, each subject in a sample is randomly chosen from some population of interest, and then two characteristics were captured from those subjects. The first characteristic is the variable x, which is a categorical variable, and the second uh, is the variable y, which is also a categorical variable. So since we have two categorical variables, wherein each of the subjects, we have identified their values for each of those two variables, then we could assign x as our row variable and y as our column variable in a two-way contingency table. So you could look back at the example of aspirin in the heart attack. There we have x as the aspirin or the grouping, either they're taking aspirin or placebo, and then the column variable is whether they had or did not have myocardial infarction. So for some notations, we have here capital I, which is the number of possible values that the variable x could take on, or consequently, this is also the number of rows. And capital J is the number of categories that the y variable could take on, and it is also obviously the number of columns. Now, for some notations, for the side of the population, where we have here I being equal to either 1, 2, 3, 4 up to capital I, and then we have here J being equal to 1, 2, 3 up to capital J. So, meaning here we have by ij, we could take on values from 1 up to capital I for this is small I, and then 1 up to capital J for this small j. So what is this pi ij? So this pi ij is a joint probability. This is the probability that the variable x has the value I, and then here the variable x has the value I, and then the variable y has the value being equal to j. This is a joint probability because you are considering the position of x, or the value of x, which is a random variable, and the value of y, which is also a random variable at the same time. So this is the probability that the xy consideration falls in the cell uh, in the position of row I and column j at the same time. So this is a joint probability because x must be equal to I and y must be equal to j at the same time. So here we have the joint probability. Then the next two notations here are for marginal probabilities. Why? Here we have pi I plus. As you can see here, I is the notation for the row placement. And then here, originally we have j, which is the placement for the column. But since we have here plus, it means you are considering uh, or not considering the column position. So this is the probability that you are in the ith row regardless of the position in the column. That is why this is a marginal probability. This is the marginal probability of x. Since we just want to know the probability that x is equal to I without consideration of the value of y. And then here is another marginal probability. This is the probability that uh, it is in the jth column, or probability that y is equal to j. Okay, so we have the joint pi ij, and then we have the marginal row probability pi I plus, and the marginal column probability, which is pi plus j. So from the previous slide, we are reserving the first subscript, first character in the subscript for the row, uh, and then the second character for the subscript for the column. But here, when we are talking about conditional probabilities, uh, that distinction is removed already. Here, we have either the column or the row in the first character, and inside the parenthesis is the other variable. So here, this is the probability that y is equal to j given that x is already at I. Or this is the conditional probability that y is equal to j given x is equal to I. So you want to determine the probability that y would take in the value of j, knowing already that the realized value of x is I. So you could have probability of I given j. If that is the case, you have here pi sub I, and then inside the parenthesis j, then that is the conditional probability of the row variable knowing the value of the column variable. Okay, so you could interchange. You need to be specific. So some would write pi sub j is equal to some value, and then parenthesis I is equal to some value, close parenthesis, just so that you would know if you are talking with j given I or I given j, because this can be quite confusing, unlike with the previous example for the joint and the marginal probabilities, wherein the position is already fixed, wherein the first one is for the row and the second one is for the column. Next, we will deal with these four concepts. As you could see, it is almost a repetition of pi ij, pi I plus j, and pi j given I. But as you could see here, they are already enclosed by braces. It just means that this is already a collection of pi ij's, or this is already the joint probability distribution, meaning you would write the value of pi 1, 1, pi 1, 2, pi 2, 1, pi 2, 2, pi 3, 1, and so on. You would list down the specific values of the probabilities for each of the pi ij's. Same goes here. You will write pi 1 plus is equal to some value, pi 2 plus is equal to some value, and pi 3 plus is equal to some value. Okay, so that is the main difference when you are enclosing them in a braces or not. If you are not enclosing, you are talking about a specific probability, meaning you need to indicate the value of j and the value of I. But here, this is a probability distribution, so you would list down all the possible values for all scenarios of i's and j's. Okay, so hopefully this is clear, but we will still have an example for this later. After going with the concept for the population side, we will be going with the sample n. So here we have nij. So n here denotes meaning it wants to have the cardinality or the number of occurrences in a certain position. So nij would be the number of observations that was inside row I, column j. Okay? So this is the number of observations cross-classified in a cell wherein it is located in row I, column j. Then we have Ni plus, meaning it is the number of observations located in the ith row regardless of the column position. Or you could express Ni plus as just the summation of all Nij's, j from 1 up to capital J. Meaning, if you want to know the number of those in the first row, then take the sum of uh, the occurrences in the first row, first column, first row, second column, first row, third column, up to the first row, capital capital J column. If you sum those, then it would be the marginal row frequency. Then, consequently, we have n plus j, which is the sum uh, in a column. Okay, so ni plus sum in a row, n plus j sum in a column. Or you could express this in the summation form, that is the sum of nij, I is from 1 up to capital I. And then of course, n is just the total number of observations. Or if you want to express it, there are three possible scenarios. You are just summing nij's for all possible values of j and all possible values of I. Or you are summing all of the marginal row totals across all i's. And then you could also see it as the sum of all the column totals. Okay? So after defining nij, ni plus, and n plus j, which is just the number of observations belonging in a certain row, column, or row and column, we will have the counterpart of the population notations that we've already discussed 2 slides ago, the pi ij, pi I plus, and pi plus j. Here we have pij. So this is the sample counterpart of pi ij. Remember, there is almost no way of knowing pi ij if we have a sample data. So we want to estimate the probability that it belongs to ith row, jth column. So how to estimate that? We could just use pij, which is how do we compute for pij? It is the number of occurrences in the ith row, jth column divided by the total number of uh, occurrences or total number of observations. So nij over n. This is just a simple concept on probability. Same goes if we want to get pi I plus, sorry, pi plus, it is just equal to ni plus over n. If you want to get p plus j, it's just n plus j over n. Of course, it will become tricky or a little bit different if we have p, j given I. Remember, this is the probability that you would locate it on column j given that it is already in row I. That is why, to compute this, it is nij over ni plus. Why? Because nij would be the number of outcomes belonging in the jth column and in the ith row. But what would change is the denominator. If you would recall here, all the denominators are equal to n because you don't have a condition. But here, they should belong in column J given that they are already in the ith row. That is why you are only considering the observations belonging in the ith row. That is why the denominator here is n plus. So for example, we have here p of I given j. So in this case, this is equal to uh, nij over n plus j. Apologies for the poor handwriting. So that is how we get pi given j. It is nij over n plus j. So we've already discussed the concept of these braces in the population part. So in the sampling part or sample part, this is just Pij inside a brace is just the sample joint distribution kasi the Pij enclosed in braces is the population joint distribution. Here we have the sample joint distribution, sample marginal distribution, and sample conditional distribution. Okay, but the concept is still the same. So here we have a two-way continuously table wherein there are two possible values for the row variable and then two possible values for the uh, column variable. Okay, so row variable and then column variable. So you could see here we have pi11, pi12, pi21, and pi22. Indicates this. You need to consider those positions to compute for the probabilities. And then to get pi 1 plus, you need to consider syempre, only row 1. And then pi 2 plus, consider only row 2. And then pi 1 plus and pi plus 2, sorry, pi plus 1 and pi plus 2, you need to consider column 1 and only column 2. Okay? To get pi 1 given 1, it's just pi 1, 1 divided by, since depending on which, this is I or this is J, you should divide it by n plus 1 or n 1 plus. So in many contingency tables, one variable, say the call variable, is usually the response variable, and the other one, which is usually the row variable x, is the explanatory variable. So there's a relationship that the row variable allegedly causes the y variable. It is not a strict condition, but in most cases, we would see those tables in those form. So if we have that situation wherein there's a cause and effect relationship, then it is informative to construct a separate probability distribution for y at each level of x, but it is not really sensible to create the probability distribution of x at each level of y, since you know that x causes y, meaning you need to take into consideration the value of x with the result or in deducing the result of y, but it is not intuitive to consider the value of y to see the result of x. Okay, so that's the reason why we have the conditional independence, because diba, in the of course, for marginal probabilities, we don't consider the other variable. We are just looking at a single variable, say either x or either y. For joint probabilities, we are looking at both x and y at the same time. But if we want to see the relationship of x going to y, then consider having this pi j given I. But if you have the other way around, meaning the variable y or the column variable causes x, then you need to compute for pi I given j, because you want to know the possibilities for the values of x given that you already know the value of y. If y causes x. But if x causes y, use this pi j given I, because knowing the value of x would uh, make you know or have more information in guessing what would the value of y be. Okay, so as a practice, or just to see if you know the concepts, using the aspirin and heart attack example, the myocardial infarction data, please obtain the sampling distribution, joint sampling distribution, the marginal sampling distribution in row, the marginal sampling distribution in uh, column, and then the conditional sampling distribution. Okay, so I would be uploading a separate PDF file containing the answers for the four sampling distributions. So you could check whether you've computed the correct values. So the last concept that we will be discussing for this first part of the video for week 1 is the concept of independence. Okay, we know that two variables are said to be statistically independent. This is the usual definition. If the conditional distributions of y are identical at each level of x, or the other way around, meaning the conditional distribution of x is identical at each level of y. Why is this the definition? Of course, meaning even if you consider the value of x, the probability of occurrences of the y values would not be affected. Or same goes with the uh, other direction. Meaning if you know the value of y, it would not affect the probability of occurrences of the values of x, since they are statistically independent. Okay? When two variables are independent, the probability of any column response j is the same in each row. It's just to reiterate the concept. Meaning, if you're computing the probability that j given I is equal to 1 is the same that probability that j given I is equal to 2 is equal to probability that j given I is equal to 3, and so on. Okay, so independence is then often referred when we are dealing with contingency tables as homogeneity of conditional distributions. Homogeneity meaning they are the same, because pi j given I is equal to 1 is equal to pi j given I is equal to 2, and so on. That is why usually when we are dealing with contingency tables, we are using the term homogeneity of the conditional distributions. Okay, so some remarks connected to independence. When both variables are response variables, meaning there's no cause and effect, or setup and then the results settings, one can describe the relationship using their joint distribution, or the conditional distribution of y given x, or the conditional distribution of x given y. So meaning there is no restriction. You could look at the joint and the conditional of y given x or x given y, since you're not imposing a direction of which one causes which. Okay, And the second remark would be, this another view. This is the usual uh, view in with the concept of independence. Instead of looking at the conditional probability, we are looking at the relationship of the joint and the marginal probability, which is uh, two variables are statistically independent if their pi ij's, or the joint probability, is equal to the product of the individual marginal probabilities across all possible values of the rows and across all possible values of the column also. Okay? So that is we have here the definition of independence based on conditional probability, but we could also view the concept of independence in terms of the relationship of the joint probability with the product of the marginal probabilities. As you could recall in your probability course, the two variables would not be independent if there's at least one I and j that uh, this equation is not true, that the product of the marginal is not equal to the joint. Okay, so thank you for listening for the first part, or part 1 of the video for week 1. So please proceed to the second part after answering the probability distributions that I've asked you to compute in the previous slide. So thank you.